Alrighty, last lesson of the sequences and series unit. We're going to go over how to expand a binomial with whole number exponents using something called Pascal's triangle. But before we get to Pascal's triangle, let's just figure out what these expansions will equal to using the old-fashioned method of distributive property. All right, number one, write each of the following without using brackets. X plus a to the exponent 0. Well, if you remember back from the exponential functions unit, as long as x plus a does not equal 0, then x plus a to the exponent 0 will equal 1, right? For part B, x plus a to the exponent 1, that will just equal x plus a. We can get rid of the exponents, or, x1 plus a1. All right, for example 2, expand x plus a squared. You know this. It's going to be x plus a times x plus a. So when you expand and collect your like terms, x squared plus 2ax plus a squared. We all agree? The coefficients of each of the terms. So that means I want the coefficient here, here, and here. So I'm going to go 1, 2, 1. You'll see, it's all part of a pattern. The powers of x, first we start with x squared, and then for the next term we decrease by 1 to x to the power of 1, which is the same as just x. And then for the last one, you see there is no x, that's really x to the power of 0, which equals 1. Alrighty, when you look at the powers of a this time, here we're starting with no a, so that's a to the power of 0. Here we have a to the exponent 1, and then the last term is a to the exponent 2. So far, so good. All right, let's do this again for x plus a cubed. This is the same as writing x plus a times x plus a squared, and you know x plus a squared is equal to x squared plus 2ax plus a squared. All right, so just expanded that. Now you have to distribute, 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 and collect your like terms. So pause the video, go ahead and try it. All right, you should have ended up with this string of 6 terms, but now when we collect all the like terms together, you should be able to see 2ax squared with ax squared. And then a squared x with 2a squared x. And last but not least, a cubed. So let's look at the coefficients of each of the terms again. Write out the pattern. Coefficients are going 1, 2, 2, sorry, 1, I totally made a mistake. Hold on, pause, sorry, made a mistake. Fix this, 3, 3. Alright, so here, also fix this, 3, 3. Okay, that's better. The powers of x are decreasing from left to right, starting with x cubed, then x squared, then x to the power of 1, then x to the power of 0. Powers of a, starting with a to the 0, then a to the 1, then a squared, then a cubed. Seeing the pattern? Try it for number 4. Alright, so this time x4, 3ax cubed plus 3a squared x squared plus a cubed x plus ax cubed plus 3a squared x squared plus 3a cubed x plus a4. Collect all of your like terms and simplify. And now we should have x4 plus 4ax cubed plus 6a squared x squared plus 4a cubed x plus a4. And write out the pattern for the coefficients. 1, 4, 6, 4, 1. The powers of x, x4, x cubed, x squared, x to the power of 1, no x at all, and then no a, a1, a2, a cubed, a to the exponent 4. So I hope you begin to see the pattern. If you go to the next page, the top of the page, there's one more example, x plus a to the exponent 5. Try that one on your own and come back and look at the solution. And here's the solution. This is the bottom half of page 2. I just filled in these rows using the investigation results from numbers 1 through 5. So as you can see, x plus a, x squared plus 2ax plus a squared, x cubed plus 3ax squared plus 3a squared x plus a cubed, and so on and so forth. Can you see the pattern in the coefficients? So over here, these coefficients, 1 and 1, they come from the coefficients of x and a, coefficients of each of the terms. So for the next row, coefficients are going to be 1, 2, 1. If there's no coefficient in front, it means that the coefficient is 1, right? We don't usually write that down. 1, 2, 1. For the next row, 1, 3, 3, 1. And for the next row, 1, 4, 6, 4, 1. I don't like the placement of that. I'm just going to fix that. And for the last row, without having to highlight, I can tell you that the coefficients are going to be 1, 5, 10, 10, 5, 1. Examine the various patterns that appear in the above expansions, then complete each of the following. In row n equals 3, so we're talking about this row right here, the exponent of x begins with 3, then increases by, so x cubed, x squared, x to the power of 1. So you can see that we're decreasing the exponent by 1 from left to right. In each row, the exponent of x increases or decreases. Well, x4, x cubed, x squared, x1, you can see that it decreases by 1 going from left to right, while the exponent of a will now a to the 0, a to the 1, a squared, a cubed, a to the 0, a1, a squared, a cubed, a4. So exponent of a will increase by 1 going from left to right. In row n equals 4, talking about this row right here, the exponent of a begins with 0, then increases by 1 going from left to right, and we end with the value of 4 as the exponent on a. So far, so good. The exponent of a in row n equals 6. So this time you have to sort of imagine if you were to continue this table for one more row, what the result would be. I think it would start with 0, and then it would also increase, based on the pattern I see, by 1 going from left to right, and it will end in the value 6. And I just highlighted here 4, 4, 6, 6 to show the relationship. In row n equals 4, so going back to this row here, for each term, the sum of exponents for each term is, so the exponent of x plus the exponent of a on each of the terms. So x to the 4, so 4 plus a to the 0, so 4 plus 0, and then 1 plus 3, 2 plus 2, 3 plus 1, 4 plus 0. As you can see, all of the exponents, their sum will be 4. All right, how about the number of terms? In row n equals 3, if you look, there's 1 term, 2 terms, 3 terms, 4 terms in total. Okay, how do I get that going from 3 to 4? I feel like all I need to do is add 1. So then the number of terms in row n equals 6 would be 7. I could just add 1. We're at the top of page 3. The triangle that you created on page 2 with the coefficients, that is what we call Pascal's triangle. It's named after the French mathematician Blaise Pascal. He started using it in the 17th century for some very lovely patterns. But actually, Persian and Asian cultures have been known to use it since the early 13th century-ish, around there. That's on the internet if you want to look it up some more. All right, so there are many, many patterns in Pascal's triangle. One such pattern, the numbers in each row, allows us to quickly expand a binomial raised to any whole number exponent. So if you haven't figured out the pattern yet, if you look at the row above, 1 plus 1 gives us that 2. Okay. 1 plus 2 gives us this 3 here. 2 plus 1 gives us this 3 here, and then 3 plus 1 gives us 4, 3 plus 3 gives us 6, 1 plus 3 gives us 4, etc. Okay. So we always add the two numbers in the row above to get the number in the row below, if that makes any sense. All right, so I just wrote that down over here. Here, n equals 0, n equals 1, n equals 2. That refers to the row numbers. I'm going to write that at the top here. So the very first row of Pascal's triangle is not the first row. It's called the n equals 0 row. All right, and if you notice here, the row number will always coincide with the second term in that row of Pascal's triangle. All right, so easy to remember. Try to figure out the numbers in row n equals 6 and n equals 7. So pause the video and come back to it. And here are rows n equals 6 and n equals 7. And as you can see, this pattern would continue on forever and ever and ever. And the nice thing about this pattern is the first half of the row is just mirrored in the next half. Okay? If it's an even numbered row, there's going to be an odd number of terms. And if it's an odd numbered row, then there's going to be an even number of terms, because if you remember from the previous example, we always had the row number plus 1 terms. I'm going to write that down. Beyond the pattern of just being able to figure out what the next number is, there are so many other patterns. We just can't get into it though, because we're kind of running out of time in this course. So instead, we're just going to use the information given to us in each of these rows to help us expand binomials really quickly without having to manually distribute everything and collect all the like terms or anything like that. So let's fill out this summary chart. Binomial expansion using Pascal's triangle. The expansion of a plus b to the exponent k is always going to have k plus 1 terms. So if the exponent is 4, then a plus b to the exponent 4, you're going to end up with 5 terms in the end. The first term of the expansion a plus b to the exponent k is a to the 0, b to the k. And the last term is, actually I'm going to just fix that, hold on one second. I'm just going to switch around the order of those exponents, my apologies. A, k, b, 0, not that it really matters, anyway. And the last term is a, 0, and b to the exponent k. The exponent of a is going to start at k, and then it's going to decrease by 1 going from left to right. The exponent of b is going to start at 0, and then it's going to increase by 1 up to k, going from left to right. The exponent sum or degree of each term is going to equal k. So if you remember in the n equals 4 row, all of the exponent sums were 4. And the coefficients of the terms can be obtained from the n equals kth row of Pascal's triangle. So in the next video, I'm going to go over in more detail how to expand a binomial just using these patterns from Pascal's triangle, and give you an opportunity to practice as well. Alright, so here are the steps to expand a binomial using Pascal's triangle. So first, get the get the coefficients from row n equals k in Pascal's triangle. Keep in mind, the first row of Pascal's triangle, the little 1 at the top, that's not row 1. Okay, that's row n equals 0. Alright, and then afterwards follow the pattern that the exponents of a begin with k, then decrease by 1, and the exponents of b begin with 0, then increase by 1. Let me go over an example over here. Expand x minus 2 to the exponent 5. So I'm going to look at row n equals 5 for the coefficients. And if I look on my previous page, I see the coefficients are 1, 5, 10, 10, 5, 1. So far so good. Now for my second step, follow the pattern that the exponents of a, so in this case, here's my a, and my b would be negative 2. So a has to start with the exponent of 5, so x 5 then x4, then x3, then x2, then x1, and then no x. With negative 2, it's going to be negative 2 to the power of 0, negative 2 to the power of 1, negative 2 to the power of 2, negative 2 to the power of 3, negative 2 to the power of 4, and negative 2 to the power of 5. Okay, so I'm going to put all of that together into my terms. So x minus 2 to the exponent 5, this is going to be, actually, let me write it on the next row. My first coefficient is 1, x5, negative 2, 0. You don't have to write that down if you don't want to, but I'm just going to put in everything. Plus 5x4, negative 2, 1, plus 10x cubed, negative 2 squared, plus 10x squared, negative 2 cubed, plus 5x1, negative 2, exponent 4, plus 1x0, negative 2, exponent 5. So as you can see, all of the coefficients are from this 1, 5, 10, 10, 5, 1, 1, 5, 10, 10, 5, 1. The pattern on the exponents of x start with 5, decrease by 1 every time, 5, 4, 3, 2, 1, and 0. The exponents on, so that was this one, then decrease by 1. The exponents on negative 2, I started with 0, and then I increased by 1 every time. So 0, 1, 2, 3, 4, 5. All right, now we need to simplify this. This is going to be, well, 1 times negative 2 to the 0 times x5, well, that's just going to be x5. Now, 5 times negative 2 to the exponent 1, that's going to be negative 10x4. 10 times negative 2 squared is positive 4. I'm just going to write it out for now, and then I'll take one more step to expand afterwards, or to simplify rather. Negative 2 cubed is negative 8. Okay. Plus 5 times negative 2 to the 4 is 16, and then x, and then plus negative 2 to the power of 5 is negative 32. I'm going to leave it in brackets, and now I can fully simplify. x5 minus 10x4 plus 40x cubed minus 80x squared plus 80x minus 32. And that's it. Once you get the hang of this, I promise it's a lot faster than expanding it all using the traditional method. Okay, in the next video, the last one, I'm just going to give you one more example and then get you to try example 3 on your own. We're at the bottom of page 4. So now that we've gone over an example of how to expand using Pascal's triangle, let's try this one more time. Expand 2y plus 3 to the exponent 6. So the first thing you should do is look at row n equals 6 for your coefficients. And take a look at your previous page. Your coefficients should be 1, 6, 15, 20, 15, 6, 1. Okay, just make sure you have 7 terms in total. 1, 2, 3, 4, 5, 6, 7. Good. All right. And now the exponents on the first term, 2y, they'll start with 6 and then they will decrease by 1 going to the right. The exponent on 3 will start with 0 and then it will increase by 1 going to the right. So what I'm going to do is I'm going to just write in the coefficients first. Leave some space. Oops. And then I'm going to fill in my powers of 2y and powers of 3. So first with 2y, 6, 2y, 5, 2y, 4, 2y, 3, 2y squared, 2y to the exponent 1, and the last term will not have an exponent of 2y, because 2y to the power of 0 is just 1 anyway. Okay. And then 3 to the power of 0, I'm not going to write anything. 3 to the power of 1, 3 to the power of 2, 3 to the power of 3, 3 to the power of 4, 3 to the power of 5, and then 3 to the power of 6. And just make sure that when you check over your terms that each of the exponents in every term, they add up to 6, which they do. Good. And now just expand everything and simplify. Go ahead. And when you come back, I'll give you the answer. Okay, I just wanted to show you this middle step. So I've almost collected my coefficients together. I just need to multiply them out. But as you can see, I have y6, y5, y4, y3, y2, y1, and no y for the last term. Okay, simplify fully. And there we have it, the last final step. And believe me, this is a lot faster than expanding it traditionally. All right, for the last example, state the fourth term of the expansion 3y minus 2 to the exponent 7. There's a couple of ways you could do this. If you want, you can expand it all out. If you want some extra practice using Pascal's triangle, go right ahead. I will write out the final answer for you there if you pause your video. And also I'm going to show you one other way after that. Sorry, I couldn't quite fit everything perfectly into one line, but here is the final long string of the expanded form. And now the fourth term would be 1, 2, 3, 4. So you could say, therefore, the fourth term is negative 22,680 y to the exponent 4. Now there is a shortcut to doing this. You can start writing out the row n equals 7 coefficients again, 1, 7, 21, 35. So now that you've reached 35, that's your fourth term. And then you know that the exponent on 3y is going to be 4. And you know that the exponent on negative 2 has to be cubed because 4 plus 3 has to equal 7. So if you put that all together, then you can say it's 35, 3y, 4, negative 2 cubed, and then simplify that to get your fourth term. And you end up getting the exact same answer. You might be wondering, how do we know that this exponent has to be 4? Well, because we know that that must go with the fourth term. And that's what we need in this question. All right, so that's it for binomial expansion, and that is it for this unit. Congratulations on completing a successful unit of flipping the classroom. The last video is just the unit outline.